Hi, folks. My name is John O'Reilly. I'm based in Galway in the west of Ireland. I work remotely for a Norwegian company called Neat, and it's an absolute pleasure to be here at Kotlin Conf in Munich today. So we're going to start today by giving a brief overview of some key concepts, and we'll dive in then to a live coding session where we build out a Compose Multiplatform application that's powered by a Koog AI agent. We'll show how we can use local tools to provide particular data needed by the agent, and we'll make use of both cloud and local LLMs. Lastly, we'll show how we can create and make use of an MCP server using the Kotlin MCP SDK. So what is an LLM? So as I said here, a type of program trained on vast amounts of data to understand, summarize, generate, and predict new content. And importantly, in the context of agentic AI and this talk, they can leverage external tools to extend their reasoning capabilities and provide grounded real-world utility. Another definition, this time from Gemini appropriately, talking again about being able to understand, generate, summarize text by analyzing massive data sets. And also makes reference to the transformer architecture, a key component of modern LLMs. So what is an AI agent? This is from Svetlana's excellent video. Describes an AI agent as a computer program that uses an LLM as its brain to solve a given task, uses tools in a loop based on feedback from the environment. Another definition from the Koog docs themselves, an AI entity that can interact with tools, handle complex workflows, and communicate with users. And Koog then is the official Kotlin framework for creating AI agents, and it's fully multi-platform ready, running on Android, iOS, JVM, and the web. Hopefully, if you haven't already, and definitely recommend watching the recording of Vadim's excellent talk on Koog yesterday, which Vadim is the tech lead for Koog. So Koog supports a range of functionality, including, for example, tool MCP support, which we'll be demonstrating today. We'll also be creating custom strategies and demonstrating Koog's KMP support. Other functionality supported by Koog includes context management, persistence, and observability and telemetry, and we'll be showing an example of the last item as well today. So Koog supports a range of different LLM providers, including the key ones, for example, like Google, OpenAI, and Anthropic, and also provides access to local models through Llama. And as of the 1.0 release yesterday, Koog also supports the LiteRT LM integration, which allows them to support running local models on Android and iOS. The initial support in the release yesterday was for Android, but I believe iOS will be coming shortly after. So this is how simple it is to start using Koog. We define an AI agent with a prompt executor, like Google, specify the model, and set a system prompt which defines the agent's persona, in this case, a climate emissions specialist. To make the agent more useful, we can add tools. In this case, for example, we're adding the Get Emissions tool, which is going to provide emissions data to the agent. Lastly, we can create custom strategies, and this allows us to control exactly how our agent loops through tool calls and handles multi-step reasoning, for example. So in the talk today, we're going to be developing a UI, and we're going to be using Compose Multiplatform. This is an open source declarative framework from JetBrains for sharing UI across multiple platforms. Next up, MCP. MCP, folks probably aware at this stage, is an open standard that allows LLMs to connect to and use external data sources and tools. And we'll be showing an example of MCP later in the talk as well. And we'll be using the Kotlin MCP SDK for that. We'll also need to get data from a road endpoint, and for that we'll be using Ktor. Just a quick show of hands at this stage. How many people here have used Ktor? OK, quite a few, great. OK, for the live coding session today, we're going to start with basically the shell of a Compose Multiplatform application, more or less as if generated using the KMP wizard in IntelliJ. We'll start by creating a basic single-turn Koog agent that connects to a cloud LLM. This has some limitations. We'll then start building out some local tools to sort of ground our agent with real data. And our local tool in this case is actually then going to use a Ktor client to get the data from the remote endpoint. We also have a Ktor server in the project as a sort of a backup in case we have any issues connecting to the internet or our endpoint's not available for any reason. So hopefully we won't need that. And lastly, the next stage then is, OK, we have a single-turn agent, but we now want to support conversational UI interaction with the user. And for that, we'll show how we can demonstrate a custom Koog strategy and then build out the associated Compose UI code as well. And lastly, we'll show how we can create an MCP server using the Kotlin MCP SDK. We'll give an example of its use in Compose Desktop and also show how it can be used in Koog as well. The talk today, the live coding session, is kind of based loosely on the Telemetry CMP sample that is in GitHub. That has a more comprehensive UI and other data sources, but definitely recommend people taking a look at that if it's of interest. And shout at this point to the excellent climate trace endpoint that we'll be making use of today. Okay, live coding. Okay, so we're going to start building out our initial AI agent. And I'm going to be using live templates for this. So initial check, is the font okay for folks? Particularly folks at the back. Okay, so this is basically where we're going to construct and configure, like I said, our climate-focused AI agent. So this is a basic agent, more or less as we showed in the slides earlier. We have a prompt executor, an LLM model, and a system prompt. One key difference here is that instead of defining the prompt executor and the LLM model directly in the agent like this, we're actually using KMP's expect actual. And just another show of hands, how many people here have used KMP? Okay, quite a few. So you're familiar with expect actual. If you're not, this provides a mechanism. In KMP, typically you want most of your code to exist in shared common code. And just to show an example here on the left, we typically have a common main in our KMP projects where, as I said, most of our code goes, and this is common code that runs across all our platforms. And then we can create an expect where we can then define the actual implementation then in source sets specific to each platform. Okay, so if we go back again, if we click on here, we can see, for example, that we're using the Gemini 2.5 Flash in this example and setting up a prompt executor with our API key, for example. And we're doing the same in the JVM for now, but we'll show an example later where we actually customize the model that we're using on particular platforms. If we go back to our agent again. Okay, so let's do an initial sanity test of this agent. Okay, so this is a simple main function that's running in on the JVM. This is basically going to create the agent and run this particular query, this prompt, show emissions for Germany in 2025. So let's run this. Okay, happily, hopefully the internet will behave for us today. Okay, so great. So we get a very comprehensive answer here. It sort of provides a lot of background information. And this is information that's sort of based on what the model has been trained on. It can conjecture, it can kind of give background information, but it's missing access to real data. So first kind of quiz, I guess. Given what we've talked about so far, any suggestions about how we would ground this agent with real data? I heard tools there, hopefully. I think I did. Okay, yeah, exactly. We can add a tool. So before we can add a tool, though, we need to provide a way to get access to the remote endpoint. And for that, we're going to be using a Ktor client. So this is going to be a basic Ktor client connected. This is the endpoint that we're connecting to. We also have a backup. As I said, if we need to run our Ktor server locally, we have a backup where we can connect localhost to that. And within a Ktor client, we need to define a HTTP client object. And this is the object we're going to be used for making requests to Ktor. Just a small note here about the fact that, as I said before, we have sort of our Gradle dependencies sort of pre-prepared for the project. And how we actually interact with Ktor then depends on the platform. And based on the Gradle dependency that we've set up, it will use the appropriate engine for that. And lastly, we define our API itself method. So a simple method, we're using our client object, we're calling it get method. This is the endpoint we're hitting. We're providing a country list and the year as parameters, making a request, and we're returning the data back. So okay, so we have an API client now, so now we can start building out our Koog tool. So tools, as I said here, are the bridge between the LLM and the real world. And we're going to define a number of data classes and classes here with various annotations. And basically, Koog will convert these into a tool called schemas that is provided to the model. So an important point here, and we'll see this in more detail when we talk about the custom strategies and so forth, is that the LLM itself does not invoke these tools. Basically, an agent like Koog will provide the necessary schema to the LLM, And the LLM will at some point decide whether it needs to call these tools. It will tell the agent about the invocation, what parameters it needs to pass, and so forth, based on the information that an agent like Koog, like in this scenario, provides. But the agent itself will actually make the call. And then we have the tool itself. Okay, so again, some more annotations, just some more metadata that Koog needs to provide the LLM. And this is sort of the main method that we implement then. And the rest of the tool call, as I said here, lifecycle, schema generation, argument parsing, result routing, is handled by Koog. So we're using our Climate API client. We're calling get country emissions and passing in the country list and the year. And as typically the case here, we're returning the result just as plain text back to the LLM, which the LLM typically knows how to parse and respond to. Okay, so now we can go back to our provider. We can add a parameter with our tool registry information. So in this particular example here, I'm instantiating these objects like Climate API client and get emissions tool directly. In a more robust application, for example, in the main climate sample, we're using Coin, using dependency injection, for example, to inject those. Okay, now that we have that, we can hopefully run our agent again. And we see, okay, fine, great, we're getting Germany's emissions in 2025 are this value here. So this is our agent running, interpreting what we're asking, determining that it needs to call the tool and making this call. So one other, this is sort of a trick question to some extent. Is there anything in the response there that looks incorrect? Okay, so I think I heard, I'm not too sure, but one important thing about LLMs is they don't really have a great grounding in terms of date and time, the current date and time. They're typically based on the sort of when they were trained. So you see Germany emissions in 25 are this. So sometimes you see are projected to be. So typically with an agent like this, in the main sort of sample this is based on, I have a specific tool for getting the date and time. But something like this, we can say the year is currently, if I can type that right, 2026, I think. Use data up to and including, this is hopefully the most typing I have to do in the talk, 2025. And if we run this again, we should hopefully see the very important past tense. Okay, Germany's emissions 25 were this, so it's got a grounding in terms of what data it is. One other change here, we're seeing this sort of very unreadable number. We can say use units of millions of tons of CO2 equivalent. If we run this again, okay, we see something that's a little bit readable. Okay, before we move on to the Compose code, just sort of take an assessment here of what we've done. We have a basic Koog agent here. We have a prompt executor model defined on a per platform basis. We have our system prompt, which we've evolved somewhat. As I said, this sort of system prompt shapes the assistant's persona, and we can set up constraints there. And all importantly, when it comes to sort of agent development, we've defined a number of tools here. We've defined one tool so far here that allows us to ground our agent with the real data. And we've done a sort of a basic console application to demonstrate that this is working correctly. Actually, one other thing I did mean to add, that I do need to add here, is an event handler. So Koog supports the concept, very similar. You might have seen Vadim mention this, making this comparison before. If you used Cato before, you had sort of the idea of installing features and plugins, for example, and Koog takes a very similar approach. And we initially installed this event handler plugin here, or feature, and we'll show another feature later on as an example. So we'll install an event handler, and we get some indication then that a tool is being invoked. So if we run this now again, we'll get our answer, but before we get the answer, we'll also see this log out here. So we can see here that the LLM decided that it needed to invoke, based on what we provided in the prompt, it needed to call get emissions tool. These were the arguments that it needed to pass. And as I said here, and we'll see that in more detail in the, when we talk about strategies, the agent then will invoke that tool for it. Okay, let's talk about Compose a little bit. So this, as I said, is a shell of a Compose Multiplatform application. This is sort of some default Compose code here, and this is the same Compose code that's going to be running on iOS, Android, and JVM in our project here. Compose Multiplatform also supports the web, and as I said, the broader example includes web, but for today we're focusing on iOS, Android, and JVM. Okay, I'm going to add some initial UI here, just to sort of, and we'll explain what it's doing, and we'll talk a little bit about some of the next steps we'll be making. So another show of hands, how many people here have used Compose? Okay, quite a few, as expected. Again, if you haven't, Compose is sort of a declarative UI framework, and what that generally means is that it's very state-driven. You define certain states, and you declare what your UI should look like in that state. And any changes in state will cause your UI to be re-rendered. So in this basic example, and like I said, we'll be evolving this, and we have some sort of temporary code in here, but right now we have sort of hard-coded inputs, get emissions for Germany, we have something indicating that the agent is running, and we have the result. We're also creating the agent directly here as well. Not something we would do in a sort of a normal application, but just for ease of illustration, we're going to construct the agent directly. Again, we also sort of, as a temporary measure, we have this launch effect here, which is basically a piece of code that will run when the UI is shown. And in this example, with sort of our initial hard-coded prompt, we're going to run the agent. This will result in this result state being updated, which in turn will result in this text element being rendered with the result. And some indication here, or using a progress indicator to indicate that the agent is running. So let's hopefully run this. Okay. Okay, and we see the first limitation of a single run agent like this. We've asked it for emissions for Germany. We haven't specified the year. It needs to know the year that we're asking for, and we've no means to tell it. So, but for now, I'm going to go back to the UI. We're going to build out the UI a little bit more before we move over to sort of supporting that conversational interaction. And I'll put in the specific date here. Let me run again. Okay, at least we see the data that we got back before. Okay, before moving over to the sort of that conversational interaction, let's just build out the UI a little bit more. We want to show sort of a chat interface with sort of different chat messages. So we're going to represent that. We're going to have a data class like this representing a chat message in our UI. The message is either going to come from the user as a sort of the prompt or a reply to the LLM for some clarifying question it might have. We have something coming from the assistant, which is from the LLM typically, and some tool invocation, for example. Okay, we have a list of messages, and that's going to represent the list of messages which we're going to show in our lazy column. But to populate those, to sort of provide the data that we need for that, we need to add some sort of callback to our agent, from our agent. So we're going to add a couple of parameters here, some indication that a tool is being invoked, and a sort of placeholder. For now, the result of this is a single run agent, and the result of that agent will be returned, and that's what we're rendering in our UI right now. But ultimately, when we create a conversational interaction, we want some callbacks so that we get intermediate callbacks or intermediate sort of responses from the agent at different points. So that's what our on-assistant message will be used for. But for the time being, we'll at least get something for the tool call. Okay, we can now go back to our UI. Okay, so we've added this. We need to add something representing, I don't know, Siri has decided to jump in for some reason. I'm not sure why. Must have said some keyword. Okay, so we need to provide then the parameters. So nothing too complicated here. We have our list of messages. When we get a tool call event, we'll add a tool message to the UI. This again is on a system message as a placeholder right now. We'll come back to that in a little while. And for now, at least, we'll update this somewhat temporary code right now in the single run agent scenario to basically run the agent as well, but provide the user and the assistant message into the UI. And as I said, this is sort of somewhat temporary. Like when we get to the point where the user is providing their own input, or when we're getting some conversation interaction going, this will be no longer be shown. So instead of showing a single text element now, we need to show something with the lazy column. Okay, and I think we're ready to run this again. Oh yes, okay, we need to provide something here for our console application. Okay, we're starting to look a little bit better. We're seeing some of the key lifecycle. We're seeing the prompt being provided by the user, or at least hard-coded for now. Seeing tool invocation, and we're seeing the final result. So before we move on to the conversational interaction, I'm just going to build out our UI a little bit more. Create a specific composable for showing each message that allows us to sort of putting on a label as to what type of message it is, what sort of color code it somewhat. And importantly, we start using this Markdown here. And Markdown basically is a nice library from Mike Pence. And the reason we're using it is that LLMs, as mentioned here, naturally produce Markdown. So this Markdown composable will render the LLM response with full formatting, as mentioned here, bold, tables, bullet lists, etc. And we'll see an example of that later. Okay, instead of using text here now, we will use the message view. We run this again. Okay, we get something that looks a little bit better. Okay, so now if we switch to sort of what we need to do to support sort of conversational interaction with the user, what I've alluded to before is the fact that we need to create a custom strategy for that. So if I go back to the provider, we can add a parameter here now to our agent, which is, if I get this right? Yes. Okay, so we can create a strategy that the agent will use. But before showing the actual strategy that we're going to use, I'm going to actually pull in here what effectively represents the default strategy that the agent will use. And what we're going to create is sort of a small enough evolution of that, but it's informative just to see how that works. So a lot of code here, but this loop, this dance that happens here between the agent and the LLM is kind of important to understand. So typically what happens here is that for a given input, we send the input to the LLM. The LLM will decide if there's tool call information, or sorry, we check, the agent rather will check the LLM response to see if there's tool call invocation required by the LLM. If there is, we extract that information, and then we execute the tools, or at least the agent executes the tools. As I said, the important point here is that the LLM itself doesn't execute the tools, but based on the information that the agent provided the LLM will decide whether to call tools or not, will provide that information to the agent, and then the agent will invoke it. We take the information we get back from our tools then, we pass it back to the LLM again. The LLM again may decide at that point to call more tools, so we check that again. And we keep looping until we get basically a text response back. Okay, this so-called assisted message. So let's run this again, and we should see exactly what we saw before. Okay, so now we're using what is effectively the default strategy that that Koog has under the hood. Just a small point in terms of the syntax here and what we're using. We're using functional strategies here. If anybody saw Vadim's talk, he was using this approach of using a kind of graph strategy. Depending on what you want to do, depending on how sophisticated your strategy needs to be, there seems to be some suggestion, there's a suggestion, I guess, that the graph strategy is a little bit more flexible, but again, it depends. I prefer the functional strategy. I think the code is a little bit more readable and easier to understand. Okay, so now let's move over to a strategy that supports conversational interaction. Okay, so a lot of code here again, but fundamentally it's the same as what we saw before with an outer loop now. So we have our inner loop before, which sort of handles agentic tool use. And now we have an outer loop basically that will run as long as the user keeps sending messages. So we have this outer loop here. In this basic example here, we'll keep looping until the user provides an empty string, for example. But the inner loop is the same as before with the sort of management of the agentic tool use. A key thing here now is that the response each time it runs, when it gets a system message that it wants to provide to the UI, it now starts to use this on a system message callback, and that's a suspend function. And a key part of this interaction here is that will suspend until the user provides an answer or a subsequent prompt, and we'll see that in more detail shortly. Okay, now we have our custom strategy there. We need to provide the on-assisted message callback that we provided. We kind of made reference to it earlier. And now if we go back to our UI, we can start to sort of build out that a little bit more. So we're going to use a Kotlin channel, basically. So user reply is a Kotlin channel. Basically, this is what's going to provide a mechanism to bridge the UI to the suspended agent strategy. And we see that in more detail here as we add in the code for the on-assisted. We're able to add in this code for the on-assisted message callback now. So key thing here, so we get the response from the LLM, from the agent. We call user_reply.receive here, which is basically going to block until user_reply.send is invoked. And as we'll see in a moment, when the user provides a response or subsequent prompt, we will call user_reply.send. That will unblock this, and the strategy loop will continue with the user's reply. Okay, we can happily get rid of this code here now. And we can add in an edit field then. Okay, so we now have a text file, standard Compose text file, where the user can now enter their, as I said, prompts and replies. And that's going to invoke onSend message. So small bit jump back here. We're adding to the list of messages, that, again, with the user prompt. And basically what we do here depends on whether it's the first time or not. If it's the first time, then we want to kick off the agent loop. We saw that strategy where we loop continuously, or loop until at least the user provides an empty string. The key thing here is that in subsequent messages, then we just send into the channel. And the suspended agent then receives that and continues the loop. Okay, so I think we are almost in a position to run this, hopefully. Okay, so now we have a prompt here. Let's remove the year. Okay, and then we see, okay, it needs the year, so we can reply with the year. We have sort of context and history here, and we can add things like and France. And it knows the context of what we mean. We mean emissions for France, and we mean in 2025, because that's what we've already been talking about here. And let's see, show in a table. Okay, and we see the markdown support, for example, here. But let's see, what if we want to compare per capita numbers? Misspelled, but spelling doesn't matter with LLMs. Okay, it can't, because it doesn't have access to population data. So another small quiz here. Based on what we've talked about so far, how would we address this? How would we provide population data to our agent? Tool calls, exactly. So let's go back to our agent. And as they say, something prepared earlier. We have a get population tool and a population client. So the population client is, again, another Ktor client where we're connecting to this endpoint to get the data. And then the tool is, again, as we saw before, just using Koog basically to wrap that around, providing information to the LLM, for example, in terms of what it expects in terms of country code and so forth. Now, if I run this again, hopefully, the LLM now knows about population data. So if we compare per capita numbers for Germany and France. I will pick on other countries shortly, so don't worry, in 2025. Okay, so we get the emission tool as before, but we also see the get population tool being invoked. And let's see again, show in a table with population data. So we see that. Okay, and then we see the data here. So we see the more meaningful per capita numbers, and we see it nicely laid out in the table, and so forth. So, okay, so I'm going to move shortly over to the MCP server. There's a few more changes I want to show here. So I talked about installing features for Koog. So another feature that we can install is Open Telemetry. It's a very nice capability, and I'm going to be using sort of the LangFuse integration here. And also want to use this as a means to, again, show KMP mechanism in place here. So install platform agent features is an expect function. Right now, in this example here, in the iOS main function, we have an empty implementation. But if we look in JVM, we see that we're using a LangFuse integration. And just a small point, as of prior to yesterday, and using the version I'm using here, that integration was only available in JVM. Thanks to Sergei Dubov from the Koog team. I was kind of giving him a hard time earlier for ruining my demo. He actually implemented support for Open Telemetry across all the platforms. So if you're using the 1.0 release, you can use, it's great to see, you can see the Open Telemetry integration running for all the platforms as well. Okay, so, but in this example, at least so hopefully demonstrating the sort of KMPs expect actual, we see this as, it's a useful capability to be able to provide per platform features for a Koog agent. Okay, so a little bit more audience participation, because I'm going to be looking at this shortly in LangFuse. I won't sort of correlate the data anymore, so I'm going to stop picking on Germany for a while. Anyone want to shout out any other countries that they're from who could use? Sorry? Italy, okay. Italy. And anywhere else? Zimbabwe. Oh, cool, okay. And hopefully I can spell this right. Probably not. Apologies if not. Is that okay? Nice. Okay. Okay, great. So now I can switch over to, I can hopefully switch over to do a refresh here. And we see, let's see if this is data. Okay, no, it's not being updated yet. Maybe we're hitting sessions, tracing. Here we go. Okay, yes, that's a relief. Okay, now so based on that, on that feature, we've enabled that LangFuse integration, and we get this nice telemetry here. We see, for example, the fact that we're using the 2.5 flash that we saw configured earlier. We see the get emissions tool with Italy and Zimbabwe, and we see the final result coming back from there, for example. So very nice. You get to see key information, you see so latency, token usage, cost, for example, and so forth. So useful capability to have. Okay, so I want to do one other thing here, which is we mentioned earlier that we can define per platform models, for example. So I'm going to switch over to a local model here using a llama. Has anyone used a llama here before? Okay, a few folks, great. So llama, basically, if you haven't before, just run this here, hopefully locally. Allows you to download and install local models running on, in this case here, for example, on the laptop. And these local models have become a lot more powerful, not just for scenarios like this, but also using with coding agents, for example. You can use a llama with Claude if you want to, and they're getting comparable. I think there's a little bit of an arms race there. They're probably always going to be a little bit behind the cloud models in terms of, at least for some of the coding scenarios. But I picked this particular model here. It's a Gwen 3.5, 35 billion parameters, sort of mixture of experts approach, sort of only 3 billion parameters used at a particular time. And it's optimized for the MacBook as well. So it's quite performant. It runs takes a similar amount of time to some of the cloud LLMs. So if we run this here again, and let me pick another country. I'm going to pick Ireland. Why not? Okay, so it's a little bit slow at the start. So basically, if I switch over, hopefully, to Activity Monitor, you see, I see a llama here. So a key constraint, I guess, with running these models is the amount of memory they use. So this is a relatively small, well, in comparison to some other models, but it's using about 20 gig of memory, so which is thankfully I have enough space for here. But it takes a little while at the first request, but then I'll put Belgium here, for example. It's quite fast on subsequent queries. And hopefully I can go over now to LangFuse. Hit refresh. Did we get our result back yet? It's a little bit slower today. Yes, okay, there we go. So we see the Gwen model being used. We see get emissions tool being called with Ireland, and then later with Belgium. We see the result coming back as well. Can anyone see anything missing from here that we saw when we were using the Gemini? Cost, yes. So if we go back to here, we can see, for example, this was how much this cost. Obviously, with the local models, they're both free and private, which is nice. Okay, and it's a fascinating area in its own self. I mean, it's weekly announcements these days in terms of new versions, new evolutions of these models, being more performant and being more capable. Okay, so where are we? Okay, so let's see. I'm going to switch tack a little bit. I'm going to talk about MCP. Get my live templates hopefully in the right way. Okay, so MCP, as mentioned, is an open standard from Anthropic that lets any LLM host discover and call tools over standard protocol. You sometimes see it described as USB-C for AI tools. In this case here, we're writing an MCP server that is going to expose the Climate Trace API as an MCP server. We're going to be running this, as I said, different protocols. We're going to be running over what's called standard I/O. It's going to be running as a local tool, MCP server, and then we can also deploy it as a remote server. In the broader sample that I have an MCP server that's deployed remotely into Cloud Run as well. So this is going to use Climate API Client. This is the same object or class that we use from our Koog tools, and it's running in shared KMP code as well. Let's see, configure server. Oh no, sorry. Okay, no, I'm in the wrong place. We have our get emissions. Okay, so we're going to use that. So first of all, we create the server object, which is sort of a object that we can use to sort of add tools to our MCP server. Just to mention a small thing, MCP supports tools, resources, and prompts in general, but I think most users you see is with tools. But in this case, for example, we're using it with tools. We're going to add a get emissions tool. There's quite a bit of boilerplate here. This is very similar. We're effectively doing the same thing as we did with our local tool earlier with Koog. We just need to provide a little bit more boilerplate for it to define the schema. And again, this is the information that the MCP host in this case will provide or will pass to the LLM. And then we have the body itself. And again, a little bit more boilerplate, parsing out the arguments. This is the key call here. We're using our climbed API, get country emissions. Again, the same call we would have made in our tool earlier. And then call tool result in. We'll wrap the response as a list of text content blocks. And the MCP host will forward these back to the LLM as tool call results. Again, as we saw, for example, in our strategy earlier with Koog. And importantly then, we need to add a main method here, which will basically set up our standard I/O transport. Okay, I'm going to use shadow jar. Hopefully folks have seen that. It sort of gives us the ability, so we're going to create a sort of an executable jar file that has all the dependencies included. Okay, and before we switch over now to Claude, I'm just going to do a sanity test on the MCP server using a very nice tool called the MCP inspector. Okay, as you can see, I ran this before, so it sort of has set up already with the sort of parameters here. We have Java jar, and this is the jar file that we just built a moment ago. Okay, hit connect, and happily see that green light come on, which is good. We can list our tools. We have to get emissions one, which we saw a moment ago. Country code list, let's try this out. We have to provide the code specifically here, 2025, and run the tool. And we see that same data we've seen a number of times coming back. Okay, so that's a useful way to do a sanity test, at least the MCP server. But what I want to do is demonstrate this in Claude Desktop initially, at least. So before we run this, just if we look in the Claude settings, and under developer settings, you see obviously that a pre-configured Claude already with the same information. There's a sort of configuration associated with Claude, configuration file, associated with Claude, and we can add our MCP servers in there. So this is the same jar file that we just built, added into Claude. So now let's go back here and say something like, okay, get per capita emissions for, let's see, Norway. I'll pick on Norway because my employer is there. Sweden, let's do, and Finland, say. If I can spell again, in 2025. Okay, so it's going to go off and get that information. Hopefully what you can start to see here is loading tools and get emissions. So as it's sort of loading that information, we can see that it's referring to the climate trace integration. It's using our MCP server. You can see get the emissions call. It's figured out obviously the 3 country codes that need to be provided, the year, and the results. And we get to see the results, and with some of the nice sort of capabilities in the sort of recent versions of Claude Desktop, you get some nice infographics as well. And for example, in the broader client again, they refer to, we can also see things like, for example, the what are called assets, what's contributing to these emissions in different countries, and sort of navigate down through those. So very useful capability to have. Okay, I'm doing okay for time, I think. Okay, so let's go back to, actually, and by the way, I forgot to switch it out, not that it really mattered, but this is, again, using that local model. It's using the Gwen model to make these queries. Okay, so let's go back here again. Let's minimize this. And this is the risky part of the talk. If I can find my nice little image. One more thing. I mentioned earlier that Koog 1.0 was released yesterday, and one of the very nice things about that is that LiteRT support, allowing us to run local models on our Android and iOS devices. Well, initially Android and soon to be iOS. So I didn't want to switch to a new version of Koog the day before the talk, so I made some changes in a branch here. Let's see, let's get stash for now. LiteRT just supports that. Switch. So this let's make sure that we have. Okay, our Gradle, while Gradle is hopefully syncing there, we'll switch over to. Okay, bear with me 2 seconds. Need to find the right place. Okay, platform Android is great. Okay, So now with the 1.0 release, we now have the ability to use LiteRT configuration. So now in my actual for Android, I have using the Gemma 4 2 billion parameter model. I'm using the executor here. The executor is configured to this path on my device. If I click on, or I think if I hold this over this, you can see the Hugging Face URL there. So you can go to Hugging Face, for example, download a particular model, upload it to your device, configure where the location of the device where that is running, and so that it basically runs a local model on your device in that case. Okay, so running devices. Okay, so this is the part that is hopefully will work okay. Hopefully, I think I have all my notifications switched off. And if we switch to the Compose app, to the actual Android application, and run this. And by the way, this is, as mentioned before, the same Compose Multiplatform code that we're running on iOS, Android, and JVM. Okay, so get emissions for Germany. So it takes a while the first time, similar to what we saw with the Llama. That's sort of the first request requires the model to be loaded. It's running on obviously a somewhat more constrained device than our laptop. Typically seeing this take sort of 15, 20 seconds for the initial request. Yes, okay, and we get back the response, and we can then do 2025 again. Now, just again, a caveat here again is that, so this came out in the 1.0 release yesterday. It's an initial early release. We see the tool invocation, by the way, happening here as well. So we see our tool being invoked, and we see the response coming back as well. So that's good to see. There are some limitations in the version that that's being used right now in terms of some of the parsing of tool responses, handling multiple tools and so forth. But it's very cool to see this available now. This is supporting Android right now. LiteRT works on iOS as well, for example, and I believe there will be in the not-too-distant future, a release of Koog that works on iOS as well. Okay, it was nice that worked. Okay, let's go back to our 2 minutes left. Go back to our slides. Okay, so what did we cover today? We created a basic single-turn AI agent, and we did a sanity test. We ran that using our console app. There were some limitations with that, of course, so we grounded our agent with real data. We created a Koog local tool and used a Cater client to get data from remote endpoints for the tool. We created an initial basic Compose UI application, running this single-turn Koog agent. We then added a sort of conversational UI based on a custom Koog strategy. We expanded the tools to support population data. We added the telemetry feature, also demonstrating use of expect actual. We used a local model on JVM. We created an MCP server and used in Cloud Desktop. And as a bonus, we demonstrated the new Koog LiteRT support running on Android using a local model, using a Gemma model on Android. And just a quick recap on what we built out today. Thank you very much.